introduce our speaker tonight. This is Jill Krezoski, and she's probably one of the only people I've ever met who has done geology both on planet Earth, all over the world, and also on Mars, as you'll get to hear tonight. Although I don't think she's been to Mars. But
I've not been there, no.
We'll see. But my understanding is she drives the camera that takes pictures on Mars. So without further ado, I'll turn it over to you, Jill, and thank you for coming.
Thank you very much. Can everyone in the back hear me? Yes. Okay, I'll try to stay by the speaker, so hopefully you'll be able to hear me. Okay, as Don mentioned, I have done geology both on Earth and on Mars. For those of you that are still trying to decide what your major is, I can only praise geology so much because it's really given me some really great opportunities. I did my undergrad in Wisconsin, and I got my master's in Ontario, Canada, at McMaster University. And from there, I worked in Pittsburgh with a geotechnical company where we did nuclear siting around the world, looking at the geotechnical aspects of that. And then I moved down to San Diego, and being a classically trained geologist, I was looking for positions. And I had a friend that said, well, why don't you check out this company in Sorrento Valley called Malin Space Science Systems. And Malin is a geologist, and he hires geologists because he likes to talk geology language to geologists, and B, we work with about 450 university professors on a daily basis that are all trying to do geological experiments on Mars. So our job is to be able to communicate with those professors at a technical level and essentially be able to run their experiments on Mars. So essentially I am a glorified lab tech because I work with the professors, tell me what to do, and then I go and do it, and then I give them the data back and they go off and write their papers with it. So it's been a lot of fun. Malin works with a bunch of engineers who we build and operate deep space cameras. So we are building a couple cameras for the Mars 2020 rover, which will launch in 2020. It's essentially another Curiosity type rover using a lot of the spare parts for the Mars 2020 rover. We're hoping to recoup a cost of about 60% of the original rover cost because we're using a lot of the same designs and a lot of the nuts and bolts that we had originally ordered for the Curiosity rover. So we are building some of those cameras. We have 4 cameras on the Mars Curiosity rover. We have the 2 mast cams, which are the ones at the top of the robotic mast. We operate the camera at the end of the robotic arm called the Mars Hand Lens Imager, also known as MALI. And we also built and operated the camera for the entry, descent, and landing. When the rover entered into the Martian atmosphere, we had a camera turn on and take a picture very quickly. So essentially we created a movie as we landed, and you can actually Google that online and see the landing. It's pretty neat, nice high-res imaging. First of its kind on Mars, so we're very proud of that. We also have a camera on the way to Jupiter, the Juno Cam, and that should be getting there in the fall of 2016, so look for some really nice pictures of Jupiter coming up. And that's actually a really neat project because majority of the pictures are going to be they'll be commanded by us, but the public will be able to choose where they want pictures taken of Jupiter. There's a small percentage of pictures that we have to take of Jupiter for science reasons, but then the public can actually choose targets on Jupiter. So that's actually a really neat new educational public outreach that we're looking forward to it. So look for that camera coming up. And then we also have the Lunar Reconnaissance Orbiter camera going around the moon, and also a couple cameras that are going around Mars as well. So lots of cameras. And so we run and operate them right here in San Diego. We call in every day to the Jet Propulsion Laboratory or to the various other services that we work with. And we coordinate and we take the pictures on Mars. So it's very neat, and it was a really neat opportunity. And I'm very glad. But if you're interested in earth science or geology or anything like that, this is just a great example of what's the sorts of things that you can do with an Earth history degree. And actually there's a new geology program that Mesa just started up. So if you are interested, you can look into that. I'm sure there's some information online about that. Yes. Okay. All right. So let's get started. So my talk is called Satisfy Your Curiosity, an update on the Mars Science Laboratory project. We have been on Mars for just over 2 years now. We landed in August of 2012, and we've got a lot of great data that we've collected since then. And I'm going to be sharing some of that with you, some of the initial conclusions that we found, and then also sort of our extended mission, where we're going. So this picture here is really neat because we took it. It's a selfie. Many of you guys probably take your own selfies using your cameras, your cell phone cameras. And what we did was the rover has a robotic arm that sticks out that can go out in front and actually look back. It's like a selfie stick looking back at the rover. And we actually took about 67 images right in the center of this photograph using the selfie, and then with that we mosaicked them together using software. Anyone can do this with Photoshop or anything. You just take a bunch of photos and mosaic them together, and with that we created the mosaic. Now, can anyone see what is missing from this image? The stick, the arm. Yeah, you can't see the arm. You can see a little bit of the shoulder, the turret here, and let me point that out right here. You can kind of see the tip of it right here, the start of it. It's cool because, I mean, when you're taking the selfie with your arm, you don't actually see a large portion of your arm. And then we had the 67 positions, so each image had a portion of the picture without the arm in it, and we used that portion to create this picture where you didn't see the arm inside of it. So we just mosaicked it out, no magic or anything, but a lot of people wonder about that. There's actually a cool video online that you can see all the different positions and how they work that out. The other portion of this image is actually taken from the mast cams. So the mast cams can go around us in a 360-degree view and take pictures of the landscape surrounding us. So we were able to mosaic the selfie together with that 360-degree view and create this really cool panorama of us on Mars. The sun is not actually something that we imaged, though. So someone put that in. Because we're not really allowed to, without solar filters in place, we're not really allowed to image the sun, but it still looks pretty cool. So this is actually probably closer to true color. Maybe it'd be a little bit more red. A lot of times we white balance the images, and that's because we make them, we filter them essentially so they look like they would on Earth. So the geologists on Earth can look at the rocks and compare them to the rocks that they actually study. So a lot of times we have we use a pixel that looks like a white pixel, and we balance it so that it looks like the sun on Earth. Yeah. So this was taken on Sol 177. Mars days are called sols, and one sol is about 24 hours and 39-ish minutes long. So that's just a fun fact. So when we first landed, we actually had to trace the Martian sols through our Earth schedule, and we ended up having to do sort of 24-hour shifts to wake up when the rover was going to sleep. So that was a challenge for the first 90 sols of the project. But since then, we have developed a lovely schedule where we get our weekends off, and the rover does its own stuff. So we tell it what to do, and we go home for the weekend, and then we come back, and it's usually done it. So it's pretty nice. So you'll notice as well in the front here, there's these two little dots here. These are little drill holes that we drilled. There's a drill on the end of the arm. And we drilled these two little holes here and got a nice little sample, which we put on board into our mass spectrometer and analyzed. What is one thing that you notice about the color of this little spot versus the rest of the surface here? It's more pale. It's actually kind of a greenish gray. It's greenish gray. And this is actually something that we're finding everywhere that we're going. If you brush away the dust or take a drill sample, everything underneath this thin dust, red dust layer is actually kind of a greenish gray, which is really neat. So when you think of Mars as being the red planet, you have to stop, pause, and say, wait a minute, if you just brush away that layer of dust, it's actually not all that red, which is pretty neat. But we're all very excited because red indicates rust or oxidation, which means that the original sediment has been altered in a certain way. And so the fact that this is still kind of a greenish gray indicates that it's still in relatively original composition. So when we're looking for evidence of life or the ingredients for life, this means that potentially those are preserved from back when these rocks were originally deposited. So right away, everyone was very excited about this color, even before we drilled it. So I'll talk a little bit more about the drill holes once we get going, but let's go ahead and get going. I really like this picture. It's a really good introductory picture. So let's get oriented on Mars here. So the upper image is a digital elevation model of Mars. You'll notice it's rectangular. That's because we've taken Mars and essentially flattened it out into a rectangle, much like you would on a map on a classroom wall, which we don't have any maps of the world in here. But we have the North Pole up here and the South Pole down here, and we have the equator kind of right in the middle. It's 0 here. And Curiosity landed in Gale Crater, which is located right by the equator right here. It's at a really unique location because it's right along this dichotomy between this sort of red, orange, yellow layer and this really blue, flat, featureless area. And what happened up here in this blue featureless area is still not really understood. Whether it was an impact that maybe remelted the northern regions, like our moon was formed by a Mars-sized impact of Earth, and then was captured in our orbit, so maybe something like that happened to Mars. Or else maybe it's just thick ocean sediments, which have created a really smooth, featureless area. So we're not really sure what's going on, but Gale is right at the line between the two, so that was one reason why this crater was chosen. The white, red, and orange are the high areas, and you can see they're very cratered. And it's really neat because when they were trying to figure out the geology of Mars and create a geologic time scale indicating what happened first, what happened second, what happened most recently, they were able to count the craters and assume that the areas with the most crater impacts has been around the longest because it's been impacted the most versus the areas that are less cratered are younger in general. But overall, the hypothesis is that Mars was very Earth-like until about 4 billion years ago. So Earth and Mars are hypothesized to have formed about 4.5 billion years ago. So it was only 500 million years of Earth-like conditions on Mars that we're looking at. And those are what we're really interested in, is what happened to those conditions. Why is Mars no longer like Earth? Why is it so dry? Why did it lose its atmosphere? What happened? So that's part of the reason why we're traveling up there, is try to create this history and try to see how, maybe the future of Earth, we can try to figure out what's going on with Earth in our future, or how we can avoid what happened to Mars in our future. But these are all questions that we're hoping to answer with a little bit more data on Mars. So also on here, some of you might be familiar with some of the previous Mars landers and rovers. Way up in the North Pole here, we have the Phoenix lander, which found ice up in the pole there. We have from the late 70s Viking 2 and Viking 1 here and here. We have Mars Pathfinder with its little rover Sojourner. We've got Opportunity here, and this landed in 2004, and its twin Spirit, which also landed in 2004. And Opportunity is actually still going. And recently, or we are just going to be completing a marathon with Opportunity. We have traveled 26.2 miles with Opportunity on Mars, which is really, we're very proud of. If we're not there yet, we will be within days. So we're very proud of Opportunity still going. Its original mission was 90 days, and that was in 2004, and it's recently celebrated its 10-year anniversary. So we're very proud of Opportunity. Unfortunately, Spirit got stuck in some sand, and we haven't heard from it in a couple years. So one out of two ain't bad. That's pretty good. Spirit completed its mission and went way beyond as well. So it deserves a rest, definitely. Okay, and then we have some these other craters here. These other black dots with white spots in the middle are. There were 4 craters initially examined for Curiosity to land within. And so those are the other 3, and we are currently examining those as potential candidates for going in on Mars 2020 as well. So they're looking at potential landing sites, but we're definitely looking at some other options as well. This figure down here is also another digital elevation model. It is showing Curiosity, the crater. You can see the crater rim here, again with the red-orange indicating high. And then this blue moat, this low spot right in the middle here with the indicating low. And then you can see this red dot right in the middle here, which is a mountain in the middle of Gale Crater. And that is what we're really interested in, is going up this mountain. So right now we're at the bottom, we're in the blue. This is a really neat infographic because in 1976, this is comparing landing ellipses and their accuracy, starting with the Viking landers and going all the way to Curiosity. So the Viking in 1976 had an accuracy range of landing of about 174 by 42 miles here. And then we have Pathfinder here, which is about 125 by 44. We have Spirit and Opportunity here. I can't quite read that. I think it's 33 by 12. Oh, excuse me, 83 by 12. We've got Phoenix, which is 2008. And then Curiosity, 2012, which is a 12 by 4 mile radius that we were able to land in on a planet thousands of miles away, millions of miles away, very far. It takes 8 months to get there. So, I mean, we were able to land within a 12 by 4 ellipse, a 12 mile by 4 mile ellipse. That's just amazing. And from there, we're building on our technology. Every time we send something up to Mars, we build on our technology, and we're getting better and better and better. More efficient. It's just really great, showing how much better we're getting. Okay, so Gale Crater, we got this mountain in the middle, so let's talk a little bit about that mountain. Here's Gale Crater, right in the middle here again. This is showing the northern lowlands and the southern highlands. So I was mentioning that dichotomy between this really low blue area that was very flat and featureless, and then this cratered high area. So we have red and yellow, our high elevation here, and we can see all the craters here. And then you have this line right through the middle here. It's very linear. We're not sure why. And then you have this sort of smooth lower area up here. And Gale Crater is right in the middle here, just right along the edge. And the hypothesis is that Gale Crater actually was filled with sediment at one point. And you can see all these craters here are full. They're basically filled in. They're soft. They have sediment up to the brim. But Gale has actually, all the sediment has blown out. It's been exhumed, and you can actually see you can see the crater floor here. And this white area indicates very, very low. So this is the lowest point in this image, other than this little white spot here. But when we're looking for water, which is one of our mission objectives, we want to go to a low spot, because just due to gravity, water collects in the low spots. So here, this is one of the reasons why we chose Gale Craters, because in that entire area, it's one of the lowest spots. And so if we're going to find water and prove that it's there, we're going to look in the low area. Okay. And here we are with the mountain in the middle. So this is Gale Crater again, up in the upper left corner here. We have the crater rim right along the edge here. We have north is in that direction there. We have this mountain right in the middle. And we have this moat around the bottom of Mount Sharp. And there's these little dark features right in here on either side of the mountain. Those are actually really mafic sand dunes. So they're really, they're basaltic in composition. They're like dark, like Hawaii type basalt. And they are sand dunes that are kind of blowing around the side of the mountain here. So you'll see these sand dunes in other images. So use them to orient yourself to where we are here. And this bottom image down here, here again is the mountain, and then there's those dark sand dunes right in front of the mountain down at the bottom here. So how big is that mountain? Well, here's a scale, and apparently my image moved here, but it's about half the height of Mount Everest. So this large gray feature here is Mount Everest. We've got Mount McKinley here, and then we have the orange is Mount Sharp, and Mount Rainier down here. So it's about 5.5 kilometers high, and it's about, the entire crater is about 150 kilometers across. And what we believe was that since Gale Crater was filled in with sediments, that this middle mountain is leftovers of those sediments. And our goal is to climb up that mountain and read the layers of the geologic history within Gale Crater and going up Mount Sharp, and to recreate the geologic history of Gale Crater, and hopefully that will really help us understand a lot about Mars. Okay, and so one of the other reasons that we chose Gale Crater, in addition to it being very low, where water would most likely collect, there was a feature here that I've outlined in blue here that looked very similar to an alluvial fan on Earth. So if you go out into the desert, Anza Borrego Desert, and you look at the mountains, they're very steep, and coming out of the canyons onto the valley floor are these fan-shaped debris piles. And usually you need water to move that sediment. It's very coarse sediment, very large grains, and wind won't blow that. Wind has been the major erosive feature on Mars for billions of years, but wind isn't going to move rocks this big. So what we're seeing from space is it's a fan-like feature, what we see from space, and so the hypothesis is maybe that's an alluvial fan. So when we look to see if it is an alluvial fan, we're going to look for big rocks and big chunks and stuff that the wind wouldn't blow and only water could move. So remember that for our future slides. Oh, and one other thing. So this is our landing ellipse, right in here, this black circle, and the star is where we landed, almost right in the middle. And we were very excited because we landed right at the bottom of this fan-shaped feature. So, bam, right there, we were there. We didn't have to drive anywhere. We could just look around us and see what's going on. Okay, briefly, I wanted to cover Curiosity's primary scientific goal because this is the point of us going to Mars. We wanted to assess a local region, aka this small area, on Mars's surface as a potential habitat for life, past or present. So one thing that's important to know about Curiosity is that we don't have, unless we find a fossil of some sort, there's no way that we're going to know if life was on Mars. We have the ability to figure out the chemistry of the rocks. We have the ability to figure out the mineralogy, so we can see if there's oxygen or potassium or silica or anything. We can see what the ingredients are. But we are carbon-based lives as we know it, and so we could find carbon, so we could find the ingredients for life, but we wouldn't actually be able to put any of those together to assess that there was something living. So the next mission, 2020, we're designing so that we could attempt to quantitatively define or find life as we know it. Mars 2020 rover is also designed to be a sample caching mission where we'll take the samples and we'll store them, and then at some later date when we have better technology we can go get them and retrieve them somehow and use those to assess them on Earth with our methods that we have on Earth. So one thing we're looking for is biological potential, so the ingredients for life, the ingredients that life needs to survive on, some sort of energy source. Water is a big one. We want to understand the geology and geochemistry of Mars, because again, we also want to figure out what happened to Mars in its geologic past to compare it to Earth and sort of see what happened. We want to look for water and weather. We also want to assess weather just for science, and also if we ever send anyone out there, we're going to want to know what sort of elements they're dealing with. And that includes radiation hazards. So if we have a radiation detector on board, and it measures radiation from the sun and also just from cosmic rays for astronaut safety, so we can design for if anyone is going to Mars, they can use that data. So it's very cool. And in our first 2 years, we have measured radiation, we've shown water, we've looked at the geology and geochemistry, and we've assessed that there are carbon, there is nitrogen, there are essentially the ingredients of life. So we'll talk a little bit about some of those here, but in the first 2 years of our mission, our prime mission, we have completed all of our mission goals. And so just the past couple months, we started our first extended mission, which is we've renewed our contract for another 2 years to continue working on Mars. It's about 2 Earth years to 1 Mars year. So we've completed 1 Mars year, just over 1 Mars year, and we're going to keep going, and we're going to go at Mount Sharp and try to get a lot more data. But we're all very proud because we've gotten so much data and so many results just within the first 2 years. So we'll get more. Okay, and I didn't want to go into detail too much on this slide, but I just wanted to show you the scientific payload. Payload is essentially what we call all the scientific instruments that we have on our Curiosity rover. So we have the very famous ChemCam here with its bright, shiny laser. Fun fact is that usually you can't actually see the laser beams. Sometimes you can see a flash of light down at the ground where it's actually ablating the minerals, but this is CGI right here, that red. Here's our cameras up here. These are the mast cams. This is what my company built and runs. Here there's one on each side there, kind of like two little eyeballs. Then we have the Molly, which is my camera. You can't see it because it's on the back side, but it's the hand lens imager. It's on the turret. And we have some other tools here. We've got a drill. This is our little drill that drilled that hole. We also have the radiation detector on board. Here's the descent imager. It's underneath the rover looking down at the ground because when we came down at Mars, it was looking down at Mars. We have our sample analysis on Mars, which is the mass spectrometer. Lots of cool instruments. We've got the REMS, which is the environmental monitoring system. So that's where we get the weather and the winds and the temperatures from. Very cool. Okay, and so once we landed, and hopefully everyone stayed up really late that night because it was only 11 o'clock when it landed. I know people in New York stayed up, so we landed amidst much fanfare, and we used this neat contraption that hopefully you've heard of, which is called the Sky Crane, which actually hovered about 40 meters above the ground and lowered Curiosity down to the ground. And it had these thrusters that made it hover above the ground that were super high powered. And it actually blew up a bunch of dust on either side of us, and it blew all that dust up onto Curiosity. So we became very dirty after we landed. So next time they'll probably pull it back just a little bit. We don't need quite as much power. They really gave it a lot of power. It was almost a little too much, a little too much. But they didn't actually know how it was going to work until they got there. Curiosity, it's about 1 ton. They say it's about as big as a Mini Cooper, and the mast is about 7 feet high. So it's pretty big, but not too big. Okay, so here we have our landing. This is where we landed. We turned on all the cameras and we looked around us and took some pictures. And here's the mountain in the background. You can see it's sedimentary layers. Along the front here you can see some layers. You can see these nice dark sand dunes right in the front if you want to get oriented. And you can see again these scour marks here that we blasted away all the sediment, that thin dust on top of it. And we looked closely at what those scours looked like with using the mast cams, and we saw this, which was very exciting because if you can look very closely, you can actually see rounded pebbles. So this is 20 centimeters, which is about 2/3 of a foot. Okay, so these are big little rocks in here. You can see little rocks that are sticking up here in this layer here, and we're very excited because when you see rounded gravel, pebble-sized rocks, that usually indicates that you have a higher energy environment. Something made those rocks travel and become rounded. So most likely you had water that was moving those rocks because air can't move something that big. The wind can't. And then see it in a rock formation right at the bottom of that weird fan set type feature that we saw. And right away you have a conglomerate on Mars, which indicates that you had water flowing down through Mars. So then we said to ourselves, well, if you have water, definitely, we've confirmed that there's water moving these rocks and rounding them. We want to go to the lowest spot, again, because water moves to the lowest area, and see if we can find where that water collected. So this is the canyon. This is north is up. We have Mount Sharp down in this lower corner right here. We've got those dark sand dunes, these linear features here. They're not colorized in this picture, but you can sort of see some sand dunes coming up through here. You have this canyon right here, which you can see really well. And unfortunately, unless you're looking really closely at the screen, it's hard to see this fan. But this is that alluvial fan that we're talking about. So we landed right at this dot here, right at the base of all those features. And we went right over here to this little dimple right here. It was only about 500 meters away, and we decided to go to that area, just a little jog over, and see what we could find. It's one of the lowest spots in the crater. So here is our landing site. You can see the mess that we made with those thrusters here. You got 2 scours on either side from those thrusters coming down, and then all of the dust that we kicked up in both directions there. And then we drove. You can see our little tracks here, right through here. And then that's Curiosity, really high albedo. It's reflecting up this is the high-rise camera, which is on one of the orbiters. It's a very high-resolution camera. And we went down into this place called Yellowknife Bay. So it's hard to see right here, but if you look very closely, kind of right here in the lighter areas, you can kind of see some weird polygons that we're calling this the bedded fractured unit. So it's sort of a low area with these weird polygons in it. So we decided to go down into Yellowknife Bay and see it almost looks like a little lake, right? With the little rim here. You see it pretty well. And immediately, this is what we saw at the bottom of Yellowknife Bay. So we found mud cracks on Mars. We went down into Yellowknife Bay and we found mud cracks. So more evidence of water. We found so much evidence of water. So we went and we looked really closely at these mud cracks, and we decided to do some drilling in this area because everyone, obviously, I was just excited right then. Everyone was super excited when we saw these pictures after we took them. So we looked really closely. This is on Mars here. These are some pictures here. These are little veins, little white veins that we saw within the mud cracks on Mars. And we took this with the ChemCam remote micro imager, which has really high resolution. It can get in really close. So we took some pictures of that. And then if you pop over here, you can see this feature right here, which is not very Martian-like. This is a Swiss Army knife because these are on Earth. These are very similar veins on Earth. So we actually analyzed these veins using the ChemCam instrument, and we found out that they're calcium sulfates. So does anyone interested in geology know what a common name for a calcium sulfate is? Gypsum, exactly. We have gypsum on Earth and we have gypsum on Mars. Very cool. So this is just a great example of how we can use Earth geology to do geology on Mars, and also a great example of how we know what's going on Mars by using Earth examples as well. So everyone is obviously very exciting. So this indicates that with mud cracks, usually it indicates an environment where you have your water drying up and leaving behind those cracks. And gypsum usually forms as an evaporate as well. It's considered a salt. Usually you find it out in the desert quite often. So from the environment that we know gypsum forms in on Earth, and also the mud cracks and also the gypsum, essentially indicated that you had a standing body of water, potentially a shallow lake, where there was evaporation occurring, and these salts were forming, and your mud cracks were forming once all the water went away. It also indicates that you have probably a similar environment to what we have on Earth. It was probably relatively pH neutral. It wasn't too acidic water. And also the temperatures are probably very, comparable at the time. Not too hot, not too cold, but where water is in its liquid form and it is evaporating. So it kind of gave us a really good indicator as to the environment that we were looking at. So we decided to go a little bit closer and drill. So again, here's those nice green colors. We're talking about kind of the greenish gray, and then we have a thin layer of this red oxidized dust on the surface here. And this is a mini drill. We like to test what we're doing first before we actually commit to the full drill. And there's no scale on here, but this looks pretty huge on this picture. However, this drill hole is only 6 centimeters deep, which is about the length of your index finger, maybe a little bit shorter than that. And the hole is the size of a dime, right here. So it's really tiny. It's not really that. It's like a drill from your garage, a really big one, but it's pretty low tech. So here's the drill bit right here. It spins, and a sample is extracted, and it kind of goes up the sides of the drill, and it goes into the turret. And then it goes through a whole sampling process, and here it ended up in the scoop here. So we are showing kind of a sample in the scoop. And then we put it into our various analyses machines on the rover, including the SAM and the ChemIn. Here's another example. So if you go back to the previous one, you see the hole is shadowed right here. So what we like to do is do an angled image where you can see the side. And this worked out so well. This is actually an image that I took, and you could see the vein going down into the rock, so everyone was also very excited about that. But it's pretty. It's very pretty. Ooh, ah. Okay, all right, that's my bragging. All done. Okay, so we put it into the Chemin instrument, which looks at the mineralogy of the rocks here, and these are two sample results here. The one on the left is we took a sample of a sand dune, sediment in a sand dune that we found on the way to Yellowknife Bay, and we ran it through this chemistry and mineralogy. And all these little lines indicate a different type of mineral. And so what we found in the sand shadow is that the minerals are all very similar to basalts, basaltic type composition where you have a lot of magnesium and a lot of iron, some feldspar. That was what we expected because that's what a lot of the surface of Mars is. But when we went over to test the Yellowknife Bay sample, we got this weird little signal right here, so this light spot, and everyone was very excited because those were clays. Those are phyllosilicate clays, and usually clays form, again, in an environment where you have a lake, fine-grained sediment, you have water trapped in those clays usually, but overall it was confirming that we had this quiet, low-energy environment where clays are forming. Very exciting. Okay, and then we stuck it in the SAM, the Sample Analysis of Mars, which is a mass spectrometer, and SAM cooked it. And these are some of the major gases that we found with SAM. So the big thing here is that this guy right here, which is H2O, many of you are familiar with, that's water. We had a really big water signal, which indicates that there is a lot of water on Mars. It's just bound up in the minerals on Mars. So then we also had some carbon dioxide. We got some oxygen. We've got some hydrogen. We've got some. These are all types of gases that you'd associate with life. With us, we didn't have a lot of oxygen, but with life as we know it, these are the type of minerals that make up life as we know it. And so, right away, first sample, we were able to confirm that there is biological potential out there. I mean, these are all minerals and elements that are familiar to us on Earth here. So at Yellowknife Bay, we found an ancient habitable environment. It had water. There was potentially an ancient river system. There was a alluvial fan. We had the mineralogy indicating that the liquid wasn't too salty. It was relatively pH neutral. You had key chemical ingredients for life are present, such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And then this is something I didn't really cover. The presence of minerals in various states of oxidation would provide a source of energy for primitive organisms. So all this red all this red dust indicates that your sediments have rusted. Any iron in them would have oxidized, and so they became reddish in color. But that blue, the greenish gray, indicates that hasn't happened yet. And so the fact that that process does happen indicates that you have some sort of energy occurring that creates that oxidation process. So the fact that you have that potential for energy, and there are life forms known on Earth to live under those types of conditions that use that energy to survive. So there is potential for that energy for organisms to, as we know it, to live up there. Okay, so that's sort of our first conclusions of our prime mission, where I said mission completed, check. That's some of our evidence. We completed basically our prime mission right next to the landing site, which worked out really well because we designed that landing site to try to maximize our mission returns. Since then, we have traveled about 8 kilometers, or about 5 miles, to this little yellow star here, taking nice pictures along the way, doing some good science along the way, but mostly we were driving very quickly. And so driving very quickly on Mars, it's about 0.1 miles an hour. So it took us about a year to get here. Hey, whoa, what are you laughing about? This is proud. So our goal is to, for the extended mission, our goal is to kind of get up right about here. So that's by next September, hopefully we're right up around here. So right now we're at the lower reaches. You can kind of see this little white unit, trace it along here. We're hanging out in this lower white unit, trying to find out more information. So this is also, you have the crater floor here. You have this white unit here, which is actually below the crater floor. These are little cliffs here that are from the crater floor on top of this little white unit here. So it's also a low area, and we're finding some really cool data. So here's those sand dunes that we were talking about before, those little dark sand dunes, and then here's a canyon that our goal is to drive up this canyon, and it kind of goes up and gets deeper and bigger as you go. But we're actually designed to handle some really high angles, like I think up to 40 or 50 degree tilt. We haven't tried it yet, so let's hope that it works. We've gotten up to 20 degrees, in some cases. The rover drivers like to play it safe, though, so we'll see. It'll be interesting. It'll be very interesting. So our goal is to kind of come around and avoid a lot of these dunes. We'll stop and scoop them and analyze them while we're there, but we'll kind of go to this little sandless area and start to head up the canyon there. Here's kind of a zoomed in version. So here you have the location where we are currently is called Pahrump Hills. So we're so close to those dunes, but we're still relatively far away if you're going 0.1 miles an hour. So we're going to kind of drive around and come up here. So we're looking, again, this is that white unit here. This is the crater floor here. Let's see. So we are now entering our first extended mission where we'll begin the traverse up Mount Sharp. And this is a little ridge here that we're going to be looking at. So one of the reasons why we chose this area and why we think Mount Sharp is so important. So if anyone has taken a geology class, I hope that you have seen a geologic time scale, which is a very convoluted time scale that includes the Jurassic, Triassic, Cretaceous, all of the time periods that go back 4.5 billion years in the Earth's history. And there's been a lot of research done. And so there's a lot of breakouts into smaller and smaller time periods where you have, maybe not 500 million years, it breaks into 25 million years and breaks into several thousand years. And it gets complex and complicated, and you have all these different ages and all these fossils, and it's crazy. Mars has the Noachian, Hesperian, and Amazonian. Three breakouts in a 4.5 billion year time span. So this one is just under 3 billion years, the Amazonian. This is the most recent time where essentially Mars is dead. It's considered dead. It's kind of the red, rusty planet. You don't have a lot of impacts. There's a little bit of volcanism. Cold, dry Mars as we know it. But before that, Mars had a very rich history, which we're only speculating about. And so we have this period where, before that, the Hesperian, where there are a lot of volcanic eruptions going on. And so if any of you have ever been to Yellowstone or anywhere where there's a lot of geothermal activity going on, if you remember, there's kind of a smell that goes along with those. Does anyone know what smell I'm talking about, where you have sulfur? What does that smell like? Rotten eggs. Yeah, sulfur, rotten eggs, yes. So during this time period, the Hesperian, you had a lot of volcanism. That was when those really huge volcanoes on Mars were really active, and there's a bunch of others around the planet as well. So you have a lot of that sulfur going out into the atmosphere, and sulfur is acidic, or can be acidic, and so that you're getting a lot of deposition of sulfates during that time period, so you have a very acidic environment. And then before that you have this, in this blue areas here, you have about 500 million years where our Mars looked like Earth. And that's where you have these clays being deposited, like the ones that we found in Yellowknife Bay. So it was a very nice water-rich environment, potentially very much like Earth. You probably could have lived there at that time based on the evidence that we found. So during this time, again, with Earth, Earth was hypothesized to have formed during a lot of impacts and asteroid impacts, and it got bigger and bigger, and those planetary bodies accreted, and Earth eventually became as big as it did. So the hypothesis is that Mars formed around the same time, and you have a lot of bombardment and a lot of crater impacts on the surface during that time period. But that is also when we had this warm, wet Mars. So we went from nice, warm, wet, probably with a really nice atmosphere here, to volcanic eruptions and a more acidic environment, and then cold, dead, dry Mars. Very sad. So remember this, clays, sulfates, and then anhydrous ferric oxides. And we're going to apply it to this figure right here, which, if you might recognize, is, again, this picture of Mount Sharp that we're going up. So here's that canyon right through the middle here. There's those dark sand dunes kind of behind. We're at Parham Hills, which is just right here. We used a machine called the Compact Reconnaissance Imaging Spectrometer for Mars, right here, CRISM, which is essentially a imaging spectrometer, so it looks for minerals on the surface of Mars. And what we saw are clays, down at the bottom here, down at the bottom of Mount Sharp. And you start going up Mount Sharp and you see sulfates here. And so just this section right here might help us confirm that entire geologic time scale, a couple billion years back at the beginning of the Mars formation. So we're really hopeful that where we're going right now is going to tell us a lot about how Mars formed. Just in the next 2 years, we're really, really hoping. It's going to be a challenge because there's a lot of rocks in just one rover. If I was up there, I could do a lot more, but unfortunately, that's hard. So I would like to avoid that, actually. Okay, so this is what Gale Crater was hypothesized to have looked like over 4 billion years ago. We see our lake sediments, we see our alluvial fan deposits or river deltas. It's essentially a lake. It's a filled-in lake. Here's a CGI. This isn't actually how it looks. This is CGI. So it'd be a lake right in the middle of your crater, very similar to all the other craters around us. There'd probably be similar lakes. But then you have the sediments around the edges eroding away through weathering, mechanical and physical weathering. Physical and chemical weathering. Mechanical and chemical weathering. There we go. And all the sediments were washing into the low spot. And they were collecting in the sediment basin. So here's our crater wall right here, another CGI, and our sediments were kind of collecting. And you can see our layers in here, this bowl. And through time, Gale Crater has been exhumed, or all the sediments have blown out of it. The hypothesis is through wind action, about 4 billion years of wind blowing and abrading those sediments and moving those sediments around. And so what we have here is we have Mount Sharp in the middle and all of our nice sedimentary layers on the edges here. So that's our current hypothesis. And as we go up Mount Sharp, we're going to try to recreate that geologic time scale. We're going to try to create the climate. We're going to try to recreate what happened within Gale Crater and what happened just with the geology of Gale Crater specifically. And so already we're finding a lot of evidence that potentially our hypothesis is true. We're already finding that alluvial fan, we're finding the lake evidence. We also have southward tilted sandstone beds on the plains. So this is just the crater, the bottom of the crater, and you have sandstone beds that are kind of this area right in the middle here, where you have your sediments flowing in from outside the crater, washing into the lake, that lake that we were showing, and leaving behind sediment deposits. And so here's some other pictures to sort of support that. We're seeing a lot of cross bedding right here, which indicates that there was a current of some sort. We're seeing a lot of planar bedding, which indicates less energy and less of a current, but still you're getting inputs of sediments. Here's some other cross strata here. And these are really fine scale. This is the scale down here. These are really fine scale laminations here. So they're indicating layers. They're indicating you're getting sediment coming in, some energy. So you do have potentially these rivers, these lakes, as we're driving by and finding that. So already we're finding really promising evidence. So very quickly, I wanted to share with you guys some results that we've gotten recently. So this is that light-toned unit right at the base of Mount Sharp that I was pointing to, this really flat-lying light unit. You can see Mount Sharp in the background there. You can see the sand dunes. So close, but so far. And then there's this overlying unit here that we're going to be driving up next. But we drilled this unit down here. It looks very similar to Yellowknife Bay. It looks like a mudstone, which is what Yellowknife Bay was. And here's our drill samples right here. We actually cracked the slab, but that didn't stop us. We kept going. And this, you can see under the Martian sunlight, looks a bit more reddish, but if you take a picture of it at night, we have some LEDs on the Molly camera. It is kind of a grayish color still, which is what we expect. Okay, and why we drilled this area is because we brushed it. There's a brush on the turret, And this is the color of the rock. This is at night. This is a nighttime image using those Molly LEDs. And it might be a little hard to see in the back, but there's these little white things in here all throughout the sample. There's one right there. They're about rice size. They're a little bit smaller than rice. So we brushed this off and we decided to drill it because it had all these little crystal laths, these little features, little crystalline features here. And so everyone again got really excited because, like at Yellowknife Bay, gypsum, which is, there's a picture up here as a really fine scale, creates those same crystal forms in basically a very similar shape. So everyone said, "Oh my gosh, we can confirm what we saw over there, and compare our results, and it'll be great." So they decided to drill. They decided to use the ChemCam instrument. They decided to use Chemin, and they found out that those little white things are not gypsum. Ooh, so the plot thickens. Ha ha ha. They're actually seeing a lot of potassium and iron, which corresponds to a mineral called jarosite, which we often find at acid mine drainage sites forming. So it indicates a very acidic environment. So you have this environment that looks similar to Yellowknife Bay, but something changed. Something was different. And so here's jarosite here. You can kind of see the little crystal faces here that you can kind of see how they compare there. So the question is, did this jarosite form when the rock was forming, which indicates that when this rock was forming, it was maybe during that volcanic period and you have all that sulfur occurring? Or did water that had a lot of iron and potassium in it flow through this rock unit at some point later, or maybe you had a lake later that came in and formed these minerals on top of that rock or within that rock? So are they primary formation or secondary formation? And this is actually something that came out last week. So this is what we're currently investigating right now on Mars. So these are the type of questions that we're investigating. So more to come, and it's getting very exciting. And stay tuned for more. Thank you. I don't know if you saw this when it was moving. It's a GIF of us. We took a selfie, and then we moved the mast, and we took another selfie. And then we just put them together. It was actually these 4 images that we retook was those. And you can also see on the ground here, little stuff's happening. So that was kind of our nerdy fun. I see one question here.
Out of curiosity,
What?
just out of curiosity, what do you think about like the Mars 1 mission?
The Mars 1 mission? No comment. It'll be interesting. Sorry, one question in the back there. Yes.
It's kind of similar, because there was an article in yesterday's paper about a woman in Chula Vista that wants to go to Mars, willing to go on a one-way ticket.
Yeah, it's going to be. I guess one study, you have to bring everything with you. One of the studies that recently came out was that if someone does go to Mars with their current technology, they'll only survive approximately 68 days. So they'll survive the 8 to 10 month trip out there and survive for 3 months. Less than 3 months. Yeah. Another question? Great, Trent?
Yes, 2 questions actually. What, if any, potential fuel sources are being investigated using mineralogy that could be extracted in order to form a future return mission to Mars? And 2, how does that sample analyze or sterilize itself?
So you're talking about the the battery power that we have for the rover? Is that what you're referring to?
What I'm talking about is what minerals can be or are being investigated that you can extract from the ground that can be used in the future as a potential fuel source for a return mission. If we send humans to Mars, we're going to want to know how to get back first. Mars 1 is kind of a joke. We've been able to go to Mars since like the 60s, but real engineering and frontier pushing, it comes from being able to come back from Mars.
Exactly.
That's where the real...
Yeah, and NASA won't send a mission until we're able to come back. So the minerals that we're finding now are basically very similar to the minerals that we have on Earth. Very similar. And that is one thing that we're establishing in this mission is the mineralogy of Mars. And so knowing that, there probably are minerals here that we can exploit. And I suspect, once mining companies find out about those, they'll be very interested in funding. But Right now, we don't. We're just establishing what those minerals are, so we haven't gone beyond that at this point. And the second, what was your second part of the question?
How does the sample analyzer or the SAM, how does that sterilize itself?
High temperatures, really high temperatures. It has to spend several days cooking until it's ready for the next sample. And even then, it's hoping for the best because even on Earth, you never know if you have contamination or not. There's no way for us to really check it. We have designed it so that ideally it is sterile, but I mean just atmospheric, wind blowing and stuff. Maybe it's supposed to be airtight, but you never know. So, yes. Sorry, one question over here.
Yeah, what is, I got two questions. What is the atmospheric pressure on Mars? And what is the average surface temperature at the equator?
Okay, average surface pressure on Mars, the atmosphere is about 1/3 of that on Earth. And so it actually depends on the time of day because when the sun is on shining, your atmosphere actually warms up and expands, very similar to your car tire. If you're driving, your air expands on the tire. So you actually have more protection during the day when your atmosphere is warmer if you're a human going out there. The average temperature at the equator during the first 90 sols, which I believe is during the winter, you're talking about maybe barely positive Celsius to about -90 Celsius or something. So you definitely want to bring a jacket. It's going to be cold. During the summer, I haven't looked at the recent results. We just went through the summer, so it'd be warmer than that. But it's survivable. You definitely want to bring a couple coats, definitely. Right back here, yeah.
As a technologist, I'm interested in who actually designed and put together the rover itself.
Sure. The Jet Propulsion Laboratory, under the direction of Caltech, designed. They created the design for the rover, and they put out the calls for proposals for all the different instruments and components and parts, and then they assembled it and put everything together. So they put out a call for proposals for the cameras, and so we answered that with our proposal for the camera, and they decided to buy our camera, and so we made it, and then we gave it to them, and they put it onto the rover and sent it all up, and so everyone else did that as well. Yeah. Right in front.
What's the latest thinking about the possibility of plate tectonics on Mars in the past?
Yeah, I think that there's a lot of evidence for plate tectonics in the past. They do have the lower portion that's very cratered. The southern highlands have a very strong magnetic reversal signal, which indicates very similarly to Earth, which with our mid-ocean ridges spreading and our parallel magnetic signatures and reversals and whatnot, they have evidence of that in that southern portion, but they don't in the northern portion. So that's part of that argument, is that why doesn't that have that? So in the back, yes.
What did happen to the water?
That's what we want to find out.
So
That's our
nobody
goal.
has a theory on it yet? It's not related to the atmosphere, the lower atmosphere?
Well, they believe it happened at the same time. That something happened where Mars lost its atmosphere and water, and they believe it's about that same time, about 4 billion years ago or so. But we don't know how or why, so that's one reason why we're investigating. And there's theories out there. I don't have them all with me or listed. I haven't studied up on them at this point. Yes?
Are there ice caps at the poles?
Yes, there are. There are both carbon dioxide and water ice caps. The carbon dioxide ones are seasonal, so they when it's warm, the carbon dioxide sublimates into the atmosphere, and when it's cold, it hardens right away onto the surface. Question?
Why Mars? Why not like Venus? Why
For
are we going forward towards the sun? Why are we moving back?
well, we have a lot of probes going to all the planets. So this Mars is the most Earth-like, so I think there's a lot of interest in it as potential source for I don't know, calling it going to at least is the next one. It's survivable if we went there.
So that's just it, like survivability.
There's a lot of other reasons. Yes, I mean it's also it's very similar to Earth, so we're hoping to learn a lot about Earth. People can actually go there, so it's manageable to attain. It's got really interesting questions regarding it. Potentially it had water. It's within the habitable zone. So there's a lot of reasons, but ultimately it's similar to us. And before we kind of go beyond that, I guess it'd be nice to understand something similar before we go really different. But we're studying everything. So yeah, on the way back.
The the crane that lowered the Curiosity, was it retrievable or is it now just?
It's gone. It cut the cords and it went and crashed.
All right, can I have the second question?
Second question, yeah.
The timescale that you have there on Mars, is that based on relative dating or have there actually been any kind of absolute dating?
Relative dating, although funny that you should ask, we actually used the sample analysis of Mars mass spectrometer to do some potassium argon dating. They found potassium and argon in the rock sources, and it was a brand new experiment that they didn't realize that they could do, and so they tried it out on Mars, and the dates actually confirmed about a 4 billion year age for the crater. So we have an absolute date on Mars. Right in front, yes.
You mentioned at the beginning 2020 new rover missions. What will be the major new capabilities the rovers are going to add to the existing?
So, let's see. There is really a new suite of instruments, and the goal is to. It's going to be chemistry, a lot of chemistry, but it'll be slightly different. There's about 20 instruments, and unfortunately, I can't recite them off at this time. But it's out there. You can go look up what those instruments are and what they're doing.
The same kind of a landing scenario.
Oh, the sonar, yeah, for landing, yes, yep. They're going to use the same technology, and because it was successful, we've proven it works. So, I'm sure there'll be slight modifications, like the thrusters might just tone it down a bit because they tossed up so much stuff onto the rover. It got really dirty. But yeah, cool. Yes.
What's the power source to move the rover and have all this analysts?
Yeah, it is very power hungry, definitely, especially with the mass spectrometer. So if you remember, Opportunity and Spirit had solar panels, and anytime there was a dust storm, their power got cut. And just over time, their power was really reduced just because dust has accumulated on those panels. So they decided to go away from that for this rover, and they're actually using a thermonuclear generator. And so that's this thing right in the back here, and it's essentially a battery that it provides power for the battery over time. It's supposed to last, I think something like 80 years, and it should last longer, but it should last really well for at least time. So we can go. All of our parts have been tested. Like none of them have failed, so we're hoping that we go much longer, 80 years hopefully.
I'm curious why they are not designing armatures that can actually dig up a fossil. What is the probability of this Curiosity actually not being able to find a fossil?
Yeah, it'd have to be at the surface because it's really difficult to dig. Right now we're managing with a 6-centimeter drill bit. It's basically superficial at this point. I'm not sure about the development for future deeper. Actually, one of the instruments on the next rover is a GPR, a ground penetrating radar. Nice job. Yeah, so we're hoping to get some subsurface data. It won't be that deep, but it should be. It's definitely better than superficial. It's better than 6 centimeters, definitely. You can just do a Google search for the landing video. It's called 7 Minutes of Terror. It's a good one. And for the Marty, the actual video where we took pictures in quick succession and showed the landing of Mars, you can just do Google like Mars landing or something like that. I'd Google it and put Marty, MARDI is the camera name. So that people put it together. All the images are down so everyone can look at them and use them and see them. Yes?
If we wanted to keep up with the new development of the next rover, would that information be open to the public? For engineering students that are interested in seeing what's going on cutting edge? Yeah,
they have news releases every now and then. I'm not sure how much of it is public at this point because they're still really in development. But I would, JPL you could sign up for their newsletter. They have a day in the news at JPL every now and then where they talk about updates. Not just it's all of their projects, but every now and then something comes out about Mars 2020. So, and if they have a press conference or something, they'll usually announce it as well. But I just visit the JPL website because it's like new information, news releases. That's how I get a lot of my information because I'm so far in the trees that I need to see the forest sometimes. And that's how I go there, and I'm like, oh, what are we doing? Oh, interesting. Yeah. Yes.
How often do you guys release photos to the public?
We release it continually. Data comes down, and we push it right out. We have a pipeline that comes out. The raw images are also on the JPL website. You can just go to the MSL website, and there's a link for raw images. A lot of times, I mean, they're reddish, right? They haven't been white balanced, so they're not pretty to look at. So some people on there's forums and whatnot, they process it and they talk about it. Unmannedspaceflight.com is where all the nerds go. So that's so all my coworkers. and hopefully some of you guys will go check it out as well. But those guys actually are the ones that they like stay up at night and they'll make products of our products. And they'll be like, oh, look what I did. And we're like, wow, that's really cool. Thanks. That's cool. Based on the data that we had collected of the site before we got there, we were right. So there are several other craters, as I pointed out at the beginning, that are potential for future landing sites for the 2020 rover. I'm not sure about the 2030 and what they're planning for where, but we've definitely established that we're doing the right thing. So hopefully we build on that. Yes?
Did you guys have any other hiccups on the mission besides the dust kicking up on the rover?
Yes, actually, one of the environmental monitoring systems, we had two. You can see one of them. This is right with the landing as well. You can see this little sort of knob sticking out from the neck here. There are two of these little sensors. They were at a 120-degree angle from each other, and they were supposed to measure the wind coming from the east, west, north, south, or just two different directions of wind monitoring, and they were also supposed to be redundant to confirm measurements that each one were taking. So one of them, something happened to it during landing. We don't know what. We took a picture of it. It looks fine. So maybe it got hit by a rock or something. I don't know while it landed. That was the major hiccup. Everything else is really, I got to knock on wood before I say, it's gone really well. Like everything has been working. It's just been really great. Yes?
Okay, this is less of a question and more of a plug because you asked this question. If anyone's interested, you should follow NASA social. There are any social media accounts, and they host these NASA social events.
Yeah.
And if you follow it, they put up every time there's a launch or event, they'll put up this not a raffle, but this opportunity for you to win a trip. You have to pay for your travel. But I won 2 years in a row, and I got to go see the Mars Atmosphere Volatile Evolutionary Explorer launch
Maven.
November 18th.
Yeah,
the Maven 18th, and we actually got a 4-day tour behind the scenes and everything, and they addressed that exact problem. Like when the dust came on, we got to go to the lab, the Skunkworks lab I think it was, and we saw how they added the coils into the solar panels. That it sends a jolt and it knocks all the dust off. So we got to go in the labs backstage and for days hang out with the astronauts and engineers. So
awesome.
Follow them and apply to those things because you can win a free trip. It's really cool. Watch and launch.
Yes.
Is there a delay? I heard there was a delay when you're when you're driving those surfaces, the distance.
Yeah, absolutely. It changes based on the distance of Mars from Earth and whatnot, but average it's about 14 minutes there, 14 minutes back. So we won't know for about 30 minutes if something happened. Usually we call that ground in the loop. So before we make a decision, we wait for the data to come back down. One of the challenges for that is that we have to either have direct connection of the rover to Earth, or we have to have the satellites, over the top of the rover getting the data, and then the orbiters transmitting that data back down. So it's hard for timing. You really have to plan something like that. What we usually do is we tell it what to do over a 24-hour period. So we spend our 8-hour workday deciding what Curiosity is going to do, then refining, and we check. We spend like 4 hours checking everything before we send it up to the rover, because obviously we don't want to break it. So first half of the day we plan what we're going to do. Second day we check. Second hour we check. Second half we check, and then we bundle it all up. We send it up. Curiosity wakes up. She goes over here, takes a picture, does this thing, does an analysis, takes another picture, and then goes back to sleep. And then the data gets, the orbiters come by and they collect the data, and then they transmit it back down to Earth while we're asleep. And then the next morning we have the data and we figure out what Curiosity is going to do the next day. So we don't quite use the delay. That really mattered when we were landing, obviously, because we really wanted to know if it worked. Yeah. Yes, follow up? Your question? Yeah.
There was an article I'm not sure if it's a rumor or not, that you found evidence of fossilized bacteria. Is it just a rumor, or is it just confirmed?
If NASA finds anything, you will find out, because that is our mission. That is what everyone is working toward, is finding this life. And so it's a rumor until we will be the first to let you guys know that it is happening, because everyone is going to freak out and be super excited about it. And of course we'll have to then test and confirm, and scientific method, everything, and before it becomes, before we can actually know for sure. But we will definitely, everyone at NASA is going to be so excited if we find that, definitely. Was there a question up in front?
I just had a question about picking the Gale landing site. I'm guessing that probably it was based on some good remote sensing data, so that when you all went to Mars, you expected to find sedimentary rock there in the central.
Yes. Yep. Yes, that is correct.
That's amazing.
Yes, we had really good orbiter data. The HiRISE camera, I think, has like meter resolution or something. So
Can you
it's
see bedding
10
from
meters.
space?
You can see bedding. You can see the bedding on Mount Sharp. Yeah, from space. So yeah, it's beautiful. Okay. All right. I see people heading out. So if you have questions, feel free to. I'll stick around for a little while and. Yeah. Thank you.